Okay, I found the. Okay.
Hello, hello. Was my mic off the entire time? I don't have time to investigate. But anyways, if ever my mic was off, then damn, just damn. CV, where is CV? Oh yeah. Yeah, basically like that, and then that's the whole CP, no? And then minus R. There you go. That's the only difference. 6564 joules. And then by the first law equation, Q is equal to wait. Q is equal to delta H, no? So same, no? Okay, we're done with example 52. Now 53. Assuming oxygen is ideal gas, calculate work done by, that is what? What is done by? Done by the system expansion. 20 grams of the gas expanding isothermally and reversibly from V1 equal to 5 liters, V2 equal to 18 liters at 20 degrees Celsius. So I have to calculate Q, W, delta U, and delta H. My hand is tired, sorry. I'll take a break. Let's resume. So this is what? Assuming ideal gas, oxygen is ideal gas. Calculate the work done by 20 grams of the gas expanding isothermally. There you go. That's the word I'm looking for. So isothermally and reversibly. This is in moving boundary work, it's case 2.2. Reversible and isothermal. So the work in this case is equal to negative nRT ln V2 over V1 equal to, if we do not have the volume, then we can say that it is also P1 over P2. And this is isothermal, no? So internal energy is 0, as well as enthalpy. The Q is negative W, no? Let's calculate for the reversible work first. Negative N, 20 grams of O2. What's the molar mass of O2? Let's convert it into mole. 32, no? 32 grams per mole. 20 over 32 is 0.625. So negative 0.625 moles times 8.314 times the temperature to 93.15 Kelvin. That is 20 degrees Celsius, no? Ln. Do we have volume? Yes. Okay. We don't have to convert them to meter cube. You already know why. I've explained that multiple times already. 0.625 times 8.314 times 293.15 times ln 18 over 5. Answer, negative 1951. Okay, so since that is our work reversible, our Q therefore is negative of the W, so this is positive 1951 joules. That is for isothermal, no? Yup. Okay. That's it for example 53. Let's check just to be sure if my answer is correct. 53, no? 53. Yup. Enthalpy. Yes. I already said it also. Okay. 54. 50 grams of NO2 initially at 17 degrees Celsius and 8 liters are compressed adiabatically. Okay. And reversibly, resulting to an increase in its temperature, increase to 500 degrees Celsius. What is this? Seven 3.15 Kelvin. Okay, so we have to calculate the final volume and work done on. Done on means compression. It makes sense. So after that, we have to calculate Q, delta U, and H. Delta H rather. Change in enthalpy. Okay, so first things first, what I want to do is convert 50 grams of NO2 to mole, no? NO2, 14 for nitrogen plus 2 oxygen atoms, so 32. 46 is the molar mass. So 50 over 46, it's an ugly decimal. Let's keep it as is for now. no? 50 over 46 mole. We'll keep that for later. In the meantime, 17 degrees Celsius, convert to SI, 290.15 Kelvin. Okay. V1, V2. Compressed adiabatically, no? In an adiabatic process, the PVT relation is T2 over T1 equal to P2 over P1 raised to gamma minus 1 over gamma equals, gamma again is the adiabatic index. Okay? And then that. Okay. We'll use the PVT relation to, because we have T2, T1, and V1. We want to know the value of V2. So T1, actually, I don't think it matters if you have to convert to SI unit, but let's give it a try. I want it in Celsius, 500 over 17, no? T2 over T1. And then V1 is 8 liters. And then P1, wait. 8 liters is yes. V2 is missing. Adiabatic index, gamma. What kind of gas is NO2? Poly, ideal. Is it ideal? At least it is polyatomic gas, no? Polyatomic gas. So the gamma is equal to 4 over 3. Is it correct? Cp, no? Over Cv. Cv is 3, Cp is 4. Correct. 4 over 3. In other words, 1.4. Sorry, 1.33. Just 4 over 3. 4 over 3 minus 1. That is... wait. Never mind. Anyways, 500 over 17 equal... We'll just wait for the time being while the calculator is processing. I'll write down example 55 already. 55. 2 moles of H2 gas. We have an answer. And it's a weird one. So this is in liters. What if it's in Kelvin? Okay, V2 is... Is my calculation correct? V1 over V2. 4 over 3. 54. We're not wrong. Okay, we're not wrong. 4.228 times 10 to the negative 4. This is in meter cube. If we want to convert it to liter, then our answer is 0.4228 liters. So yes, my recommendation from here is that temperature should be in Kelvin. You could put it in meter cube, but it's gonna be in scientific notation because of how small it is, no? So Kelvin and liter. But Kelvin and meter cube for uniformity is okay. Okay? Just like what we did. Okay, we're not that's not the end of example 54, no? We have to calculate for, since this is adiabatic, no? In adiabatic process, delta U is N CV delta T, T1, T2, no change, nothing changed there. We have Q. How about work? Nothing is zero. Wait, is the work, is the process reversible? Yes. Adiabatic and reversible process, this is in other words called isentropic. So isentropic, work reversible, and adiabatic is equal to P2 V2 minus P1 V1 over gamma minus 1. In other words, nRT2 minus nRT1 over gamma minus 1. Okay? So, nRT2 minus T1 over gamma minus 1. Whatever applies most conveniently. That is for the work reversible, no? That is what we're looking for? Is that? No. This is what we're looking for. Let's see what we can do. For Q, what is Q? Q is 0 because it is adiabatic. Okay? So from the first law equation, the delta U equal to Q plus work, delta U equal to work. So these are the same in an adiabatic process. So let's start with delta U. Delta U equal 50 over 46 mole times CV. Where do we get CV and CP? We don't have any information, no? We cannot use the we cannot use this one, no? Because apparently in the table, the same table that I am basing my constants on, it does not have information for NO2. So what we do as a last resort is by the table. NO2 is a polyatomic gas, no? Ideal polyatomic gas. So CV is wait. We're gonna assume ideal gas. Gas is ideal. So that we can say that CV for ideal polyatomic gas is 3R and CP is equal to 4R. Yes, rightly so. So from there, what's the formula again? CV. CV. 3 times R, 8.314, no? Let's stick with joules. And then dt T2 minus T1. Temperature 2 and 1 are given. So 773.15 minus 290.15. Solve. There you go. And then, okay, so this happens to be equal to the work also. But that's not what we're looking for. What is Q? Q is equal to 0 joules because this is a adiabatic process. And enthalpy equals what? Mole times Cp. This time, Cp is for R, no? For ideal polyatomic gas. Then times quantity, temperature 2 minus 1. Minus temperature 1. Okay. $17,459 joules. What if we want it in calories? 13,095, 4.1841. 3130 calorie. This one, 17,459 is 4173 calories. Check answers. We're done for example 54. 13,095, 17,459. Okay, so the hardest part here so far is calculating for the volume. No? I got confused in the part where so this is wrong, no? We experimented a while ago. Celsius, do not ever put Celsius. Even though it's tempting to think that they could cancel, it's just gonna mess you up. Okay? Example 55. So 2 moles of H2 gas, hydrogen diatomic gas. Gamma is 1.4 at 10 atmosphere originally, so this is P1. 400 degrees Celsius, this is T1, was allowed to expand adiabatically until P equals 1 atmosphere. So, calculate final temperature, the work, the heat, internal energy, and the change in enthalpy for a reversible process. Let's do this first before I introduce the other scenario. Okay, for reversible process, adiabatic reversible, so what we're dealing with is an isentropic process. So the work, therefore, is equal to isentropic process. This is P equals K V raised to negative N. C V raised to negative N. Yep, sounds about right. Okay, so for reversible work, this is our P external. Okay, we're given value of gamma until pressure is 1 atmosphere. So this is P2. Let's use the PVT relation for adiabatic process. Whip it out again. T2 over T1 equal to P2 over P1 raised to gamma minus 1 over gamma equal to V1 over V2 raised to gamma minus 1. We're only going to use P and T, this one, no? So T2 is what we're going to look for. 400 degrees Celsius in Kelvin, so just add, equal to P2. P2 is 1 atmosphere, 101,325. Might as well convert it into SI, just to be safe. And then P1 is 10 atmosphere. In Pascal is just multiply by 101,325. Oh yeah, by the way, conversion factor, 1 bar equal to how many atmosphere? 0.9 freak. 983, 9923. That's the best that I can do. 1 atmosphere though is equal to 1.01325 bar, I think. 386, 9, 386, what? 986,923. 986,923. Okay, I'm cooked. Anyways, going back. The gamma is what? 1.4, no? Minus 1 over 1.4. Okay, shift solve. Actually, the 101,325 just cancels, so just 1 over 10 will be okay. .66 Kelvin. Okay. We have already found the final temperature. What now? Do we have P external? I don't think so, no? Um, How about delta U first? Let's find this first. Internal energy change in an adiabatic process is N C. Oh yeah, adiabatic process. Q equals 0 joules for adiabatic process. There is no heat transfer basically, no? N CV dt. Two moles. What is our CV? What is 1.4 in 7 over 5? This is diatomic, yeah. Ideal diatomic gas. CV equal to 7 over 2 rather. And then CP is equal to 5 over 2R. 7 over 2R. So gamma is equal to 7 over 5 equal to 1.4. We were able to trace. It makes sense. CV therefore is 5 over 2R. R being what? 8.314 since we want the unit of delta U in joules, no? dt, T2, what? T2 is what? Wait, do we have temperature? We do. T1, T2, 348.66 minus T1, 4, 5, 6, 673.15. Huh? Is that correct? 400 plus 273.15. Yup. Okay, so 5 times 8.314 times quantity 348.16 minus 673.15. This is negative 13,510 joules delta U. For an adiabatic process, no? Delta H, how about delta H? N CP T2 minus T1. N is what? 2 moles, no? Eight point three one four. Hot potato. 7 over 2, 8.314, and then this, just copy paste. Negative 18,914 joules. There's this ancient is this valid? Wait. HUW H minus, let's try 18,914 minus negative 13,510 negative 5404 for the work. H minus U. Let's just see if it works, but it's definitely not right. Probably. It's definitely wrong. Let's convert this to calorie. The answer key is in calorie. 3,228. To 9 rather. Approximate, sure. The answer key is negative 3224. For delta H, how about for delta H? Negative 4521. In the answer key, it's 4513. It's pretty far. Pretty far. Yeah, it's pretty far, but it's still approximate. Reasonably okay. That's the reason why I'm very stuck in this problem. I did not realize that this is reversible, no? So reversible, it's not that you use. You don't use P external. You use P2 V2 minus P1 V1 over gamma 1. I already wrote that earlier, this one. But it wasn't used in this example 54. Now that I needed it, I did not realize the need for it. So how do we have pressure? Yes, we do, but not the volume, no? We don't have volume 1 and 2. So what do we do? P, remember, in an ideal gas equation of state, PV equal nRT, no? So P equal to nRT over V. So P2 could be expressed as nRT over V2. So basically V2 cancel, no? Okay, N is 2, R is 8.314. Negative 13,489 joules. In calories, this is negative 3224. Let's see. Negative 3224. Tama. Correct. Bueno. And how? So, how? Okay, we're done with all the problems. Yay. Yay. It is 7:30 a.m. My exam is 12:45 p.m. I have another exam. Okay, bye-bye.